Well, it's a real pleasure to be here and to have a chance just to meet with you and talk about some of the problems that we're facing. Now, some of these problems are local, some are national, some are global, but they're all tied together. They're tied together with arithmetic, and the arithmetic isn't very difficult. And what I hope to do is I hope to be able to convince you that the greatest shortcoming of the human race is our inability to understand the exponential function. So you say, well, what's the exponential function? This is a mathematical function that you would write down if you're going to describe the size of anything that was growing steadily. If you had something growing 5% per year, you'd write the exponential function to show how large that growing quantity was year after year. And so we're talking about a situation where the time that's required for the growing quantity to increase by a fixed fraction is a constant. 5% per year, the 5% is a fixed fraction, the per year is a fixed length of time. Now that's what we want to talk about, it's ordinary steady growth. Well, if it takes a fixed length of time to grow 5%, it follows it takes a longer fixed length of time to grow 100%. Now that longer time is called a doubling time. We need to know how you calculate the doubling time, and it's easy. You just take the number 70, divide it by the percent growth per unit time, and that gives you the doubling time. So our example of 5% per year, you divide the 5 into 70, you find that growing quantity will double in size every 14 years. Well, you might ask, where did the 70 come from? The answer is it's approximately 100 multiplied by the natural logarithm of 2. If you wanted the time to triple, you'd use the natural logarithm of 3. So it's all very logical. But you don't have to remember where it came from if you'll just remember 70. Now, I wish we could get every person to make this mental calculation every time we see a percent growth rate of anything in a news story. For example, if you saw a story that said things have been growing 7% per year for several recent years, you wouldn't bat an eyelash. But when you see a headline that says crime has doubled in a decade, you say, my heavens, what's happening? Well, what is happening? 7% growth per year. Divide the 7 into 70, the doubling time is 10 years. But notice, if you're going to write a headline, you never write crime growing 7% per year because most people wouldn't know what it really means. Now, do you know what 7% really means? Let's take another example from Colorado. The cost of an all-day lift ticket to ski at Vail has been growing about 7% per year ever since Vail first opened in 1963, and at that time you paid $5 for an all-day lift ticket. Now, what's the doubling time for 7% growth? 10 years. So what was the cost 10 years later in 1973? 10 years later in 1983, 10 years later in 1993. And what do we have to look forward to? Now this is what 7% means. Most people don't have a clue. Well, let's look at a generic graph of something that's growing steadily. After one doubling time, the growing quantity is up to twice its initial size. 2 doubling times, it's up to 4 times its initial size. Then it goes to 8, 16, 32, 64, 128, 256, 512. In just 10 doubling times, it's 1,000 times larger than when it started. And you can see, if you tried to make a graph of that on ordinary graph paper, the graph will go right through the ceiling. Now let me give you an example to show the enormous numbers you get with just a modest number of doublings. Legend has it that the game of chess was invented by a mathematician who worked for a king. The king was very pleased. He said, I want to reward you. And the mathematician said, my needs are modest. Please take my new chessboard and on the first square place 1 grain of wheat. On the next square double the 1 to make 2. On the next square double the 2 to make 4. Just keep doubling till you've doubled. For every square, that will be an adequate payment. Well, we can guess the king thought, this foolish man. I was ready to give him a real reward. All he asked for is just a few grains of wheat. Well, let's see what's involved in this. We note there are 8 grains on the 4th square. Now, I can get this number 8 by multiplying 3 2's together. It's 2 times 2 times 2. It's 1 2 less than the number of the square. Now, that follows in each case. So, on the last square, I'd find the number of grains by multiplying 63 2's together. Now let's look at the way the totals build up. When we have 1 grain on the first square, the total on the board is 1. We add 2 grains, that makes a total 3. We put on 4 grains, now the total is 7. 7 is a grain less than 8. It's a grain less than 3 2's multiplied together. 15 is a grain less than 4 2's multiplied together. Well, that continues in each case. So when we're done, the total number of grains will be 1 grain less than the number I get multiplying 64 2's together. And my question is, how much wheat is that? You know, would that be a nice pile here in the studio? Would it fill the building? Would it cover the county to a depth of 2 meters? How much wheat are we talking about? The answer is it's roughly 400 times the 1990 worldwide harvest of wheat. Now that could be more wheat than humans have harvested in the entire history of the earth. And you say, how'd you get such a big number? Well, it was simple. We just started with 1 grain, but we let the number grow steadily till it had doubled a mere 63 times. There's something else that's very important. The growth in any doubling time is greater than the total of all of the preceding growth. For example, when we put 8 grains on the 4th square, the 8 is larger than the total of 7 that were already there. When we put 32 grains on the 6th square, the 32 is larger than the total of 31 that were already there. Every time the growing quantity doubles, it takes more than all that you'd used in all of the preceding growth. Now, let's translate that into the energy crisis. Here's an ad from the year 1975, and it asks the question, could America run out of electricity? America depends on electricity. Our need for electricity actually doubles every 10 or 12 years. That's an accurate reflection of a very long history of steady growth of the electric industry in this country, growth at a rate of around 7% per year, which goes with doubling every 10 years. Now, with all that history of growth, they expected the growth would just go on forever. Fortunately, it stopped. Not because anyone understood the arithmetic, it stopped for other reasons. But let's ask, what if? Suppose the growth had continued. Then we would see here the thing that we just saw on the chessboard. In the 10 years following the appearance of this ad, in that decade, the amount of electrical energy that we would have consumed in this country would have been greater than the total of all of the electrical energy we had ever consumed in the entire preceding history of the steady growth of that industry in this country. Now, did you realize that anything as completely acceptable as 7% growth per year could give such an incredible consequence that in just 10 years you'd use more than the total of all that had been used in all of preceding history? Well, that's exactly what President Carter was referring to in his famous speech on energy. One of his statements was this. He said, and in each of those decades, more oil was consumed than in all of mankind's previous history. Now, by itself, that's a stunning statement. Now you can understand it. The President was telling us a simple consequence of the arithmetic of 7% growth each year in world oil consumption, and that was the historic figure up until the 1970s. Now, there's another beautiful consequence of this arithmetic. If you take 70 years as a period of time, and note that that's roughly 1 human lifetime, then any percent growth continued steadily for 70 years gives you an overall increase by a factor that's very easy to calculate. For example, 4% per year, you find the factor by multiplying 4 2's together. It's a factor of 16. Now, a few years ago, one of the newspapers here in Boulder quizzed the 9 members of the Boulder City Council and asked them, what rate of growth of Boulder's population do you think it would be good to have in the coming years? Now, the 9 members of the Boulder City Council gave answers ranging from a low of 1% per year. Now, that happens to match the present rate of growth of the population of the United States. We are not at 0 population growth. Right now, the number of Americans is increasing by more than 3 million people every year. No member of the City Council said Boulder should grow less rapidly than the United States is growing. Now, the highest answer any council member gave was 5% per year. Well, you know, I felt compelled. I had to write him a letter and say, did you know that 5% growth for just 70, I can remember when 70 years used to seem like an awful long time. It doesn't seem so long now. Well, that means Boulder's population would increase by a factor of 32. That is where today we have 1 overloaded sewer treatment plant. In 70 years, we need 32 overloaded sewer treatment plants. Now, did you realize that anything as completely all-American as 5% growth per year could give such an incredible consequence in such a modest period of time? Our city council people had zero understanding of this very simple arithmetic. Well, a few years ago, I had a class of non-science students. We were interested in problems of science and society. We spent a good deal of time learning to use semi-logarithmic graph paper. It's printed in such a way that these equal intervals along the vertical scale each represent an increase by a factor of 10. So you go from 1,000 to 10,000 to 100,000, and the reason you use this special paper is that on this paper a straight line represents steady growth. We worked a lot of examples. I said to the students, let's talk about inflation. Let's talk about 7% per year. It wasn't this high when we did this. It's been higher since then, and fortunately it's lower now. And I said to the students, as I can say to you, you have roughly 60 years life expectancy ahead of you. Let's see what some common things will cost if we have 60 years of 7% annual inflation. Well, the students found that a 55-cent gallon of gasoline will cost $35.20. $2.50 for a movie will be $160. The $15 sack of groceries that my mother used to buy for $1.25, that'll be $960. A $100 suit of clothes, $6,400. A $4,000 automobile will cost $250,000, and a $45,000 home will cost nearly $3 million. Well, I gave the students these data. These came from a Blue Cross Blue Shield ad. The ad appeared in Newsweek magazine. And the ad gave these figures to show the cost escalation of gallbladder surgery. In the year since 1950, when that surgery cost $361. I said, make a semi-logarithmic plot. Let's see what's happening. The students found that the first 4 points lined up on a straight line whose slope indicated inflation of about 6% per year. But the 4th, 5th, and 6th were on a steeper line, almost 10% inflation per year. Well, then I said to the students, run that steeper line on out to the year 2000. Let's get an idea what gallbladder surgery might cost. The answer is $25,000. The lesson there is awfully clear. If you're thinking about gallbladder surgery, do it now. In the summer of 1986, the news reports indicated that the world population had reached the number 5 billion people, growing at the rate of 1.7% per year. Well, your reaction to 1.7 might be to say, that's so small. Nothing bad could ever happen at 1.7% per year. So you calculate the doubling time, you find it's only 41 years. More recently, in 1999, we read that the world population had increased from 5 billion to 6 billion people. The good news is that the growth rate had dropped from 1.7% per year to 1.3% per year. The bad news is that in spite of the drop in the growth rate, the world population today is increasing by something over 80 million people every year. Now, if this modest current 1.3% per year could continue, the world population would grow to a density of 1 person per square meter on the dry land surface of the earth in just 780 years, and the mass of people would equal the mass of the earth in just 2,400 years. Now, we can smile at those. We know they couldn't happen. This one makes for a cute cartoon. The caption says, "Excuse me, sir, but I am prepared to make you a rather attractive offer for your square." Now, there's a very profound lesson in that cartoon. The lesson is that zero population growth is going to happen. Now, we can debate whether we like zero population growth or don't like it. It's going to happen, whether we debate it or not, whether we like it or not. It's absolutely certain people could not live at that density on the dry land surface of the earth. Therefore, today's high birth rates will drop. Today's low death rates will rise till they have exactly the same numerical value. That will certainly be in a time short compared to 780 years. So maybe you're wondering what sort of options are available if we wanted to address the problem. In the left-hand column, I've listed some of those things that we should encourage if we want to raise the rate of growth of population and in so doing make the problem worse. Just look at the list. Everything in the list is as sacred as motherhood. There's immigration, medicine, public health, sanitation. These are all devoted to the humane goals of lowering the death rate. And that's very important to me if it's my death they're lowering. But then I have to realize that anything that just lowers the death rate makes the population problem worse. There's peace, law and order. Scientific agriculture has lowered the death rate due to famine. That just makes the population problem worse. The 55-mile-an-hour speed limit saved thousands of lives. That makes the population problem worse. Clean air makes it worse. Now, in this column are some of the things we should encourage if we want to lower the rate of growth of population and in so doing help solve the population problem. Well, there's abstention, contraception, abortion, small families, stop immigration, disease, war, murder, famine, accidents. Now, smoking clearly raises the death rate. Now, that helps solve the problem. Well, remember our conclusion from the cartoon of 1 person per square meter. We concluded that zero population growth is going to happen. Let's state that conclusion in other terms and say it's obvious nature is going to choose from the right-hand list, and we don't have to do anything except be prepared to live with whatever nature chooses from that right-hand list. Or we can exercise the one option that's open to us, and that option is to choose first from the right-hand list. We've got to find something here we can go out and campaign for. Anyone here for promoting disease? We now have the capability of incredible war. Would you like more murder, more famine, more accidents? Well, here we can see the human dilemma, because everything we regard as good makes the population problem worse. Everything we regard as bad helps solve the problem. Now, there is a dilemma, if ever there was one. And the one remaining question is education. Does it go in the left-hand column or the right-hand column? Well, I'd have to say thus far it's been firmly in the left-hand column. It hasn't done much about reducing ignorance of the problem. And nature is already choosing from that right-hand list. You've read about the AIDS epidemic that's devastating the continent of Africa. I had a friend back from Zimbabwe. People, he said, are dying on the streets. Nature's taking care of the problem. So where do we start? Well, let's start in Boulder, Colorado. Here's a graph of Boulder's population. There's the 1950 U.S. Census figure, 1960, 1970. In that 20-year period, the average growth rate of Boulder's population was about 6% per year. Now, we've been able to slow the growth somewhat. There's the 2000 census figure. Well, I like to ask the people, let's start with the 2000 census figure, go another 70 years, one more human lifetime, and ask, what rate of growth of Boulder's population would we need in that 70 years so that at the end of 70 years, Boulder's population would equal today's population of your choice of major American cities? Well, Boulder in 70 years could be as big as Boston is today if we just grew 2.58% per year. Now, if we thought Detroit was a better model, we'll have to shoot for 3.27% per year. And remember the historic figure on the preceding slide, 6% per year. If that could continue for one lifetime, Boulder would be larger than Los Angeles. Now, this isn't Boulder plus Broomfield, Louisville, Lafayette, the other towns in the county. This is just Boulder. Well, it's obvious you couldn't put Los Angeles in the Boulder Valley. Therefore, it's obvious Boulder's population growth is going to stop. Now, the only question is, will we be able to stop it while there's still some open space, or will we wait until it's wall-to-wall people and we're all choking to death? Now, it's interesting to read what the boosters say. Some years ago, we read that doubling its population in 10 years, Boulder is indeed a stable community. What in the world are they talking about? You're going 100 miles an hour, 7% growth per year, doubling in less than 10 years, and someone makes the idiotic statement that we're stable. We're standing still. We're not moving. They don't even understand the meaning of the words that they put down on paper. Well, every once in a while somebody says, but you know, a bigger city might be a better city. And I have to say, wait a minute. We've already done that experiment. We don't need to wonder what will be the effect of growth on Boulder, because Boulder tomorrow can be seen in Los Angeles today. And for the price of an airplane ticket, we can step 70 years into the future and see exactly what it's like. And what is it like? Well, here's an interesting headline from Los Angeles. That headline probably has something to do with this headline. So, well, how are we doing in Colorado? The Denver Post tells us that we're the growth capital of the USA and proud of it. The Rocky Mountain News tells us to expect another 1 million people in the Front Range in the next 20 years. But in the Post there was an interesting story. Someone was quoted as saying Colorado has a 3% growth rate. That's like a third world country with no birth control. We send foreign aid, family planning assistance to countries that have smaller population growth rates than Colorado has. Well, as you can imagine, growth control is very controversial, and I treasure the letter from which these quotations are taken. Now, this letter was written to me by a leading citizen of this community. He's a leading proponent of controlled growth. Now, controlled growth just means growth. This man writes, I take no exception to your arguments regarding exponential growth. I don't believe the exponential argument is valid at the local level. So you see, arithmetic doesn't hold in Boulder. Now I have to admit, that man has a degree from the University of Colorado. It's not a degree in mathematics, in science, or in engineering. Let's look now at what happens when we have this kind of steady growth in a finite environment. Bacteria grow by doubling, and one bacterium divides to become 2, the 2 divide to become 4, the 4 become 8, 16, and so on. Suppose we had bacteria that doubled in number this way every minute. Suppose we put one of these bacteria in an empty bottle at 11 in the morning and then observe that the bottle's full at 12 noon. Now there's our case of just ordinary, steady growth. It has a doubling time of 1 minute. It's in the finite environment of one bottle. I want to ask you 3 questions. Number 1, at what time was the bottle half full? Well, would you believe 11:59, 1 minute before 12, because they double in number every minute. And the second question, if you were an average bacterium in that bottle, at what time would you first realize that you were running out of space? Now think about this. This kind of steady growth is the centerpiece of the national economy and of the entire global economy. Think about it. Well, let's just look at the last minutes in the bottle. At 12 noon, it's full. 1 minute before, it's half full. 2 minutes before, it's a quarter full, then an eighth and a 16th. Let me ask you, at 5 minutes before 12, when the bottle's only 3% full and is 97% open space just yearning for development, how many of you would realize there was a problem? Now, in the ongoing controversy over growth in Boulder, someone wrote to the newspaper some years ago and said, look, there isn't any problem with population growth in Boulder because, the writer said, we have 15 times as much open space as we've already used. So let me ask you, what time was it in Boulder when the open space was 15 times the amount of space we'd already used? And the answer is, it was 4 minutes before 12 in Boulder Valley. Well, suppose that at 2 minutes before 12, some of the bacteria realize that they're running out of space, so they launch a great search for new bottles. And they search offshore, on the outer continental shelf, in the overthrust belt, and in the Arctic, and they find 3 new bottles. Now, that is a colossal discovery. That discovery is 3 times the amount of resource they ever knew about before. They now have 4 bottles. Before the discovery, there was only 1. Now, surely, this will give them a sustainable society, won't it? Well, you know what the third question is. How long can the growth continue as a result of this magnificent discovery? Well, let's look at the score. At 12 noon, 1 bottle's filled, there are 3 to go. 12:01, 2 bottles are filled, there are 2 to go. And at 12:02, all 4 are filled, and that's the end of the line. Now, you don't need any more arithmetic than this to evaluate the absolutely contradictory statements we've all heard and read from experts who tell us in one breath we can go on increasing our rates of consumption of fossil fuels. In the next breath they say, but don't worry, we'll always be able to make the discoveries of new resources that we need to meet the requirements of that growth. Well, some years ago in Washington, our Energy Secretary observed that in the energy crisis, we have a classic case of exponential growth against a finite source. So let's look at some of these finite sources. From the work of the late Dr. M. King Hubbard, we have here his semi-logarithmic plot of world oil production. The line's been approximately straight for over 100 years, clear up here to the year 1970. Average growth rate, very close to 7% per year. So it's logical to ask, well, how much longer could that 7% continue? Well, that's answered by the numbers in this table. In the top line, the numbers tell us that in the year 1973, world oil production was 20 billion barrels. The total production in all of history, including that 20, was 300 billion. The remaining reserves, 1,700 billion. Now, those are data. The rest of this table is just calculated out. Assume that the historic 7% growth continued steadily each year following 1973, exactly as it had been for the preceding 100 years. Now, in fact, the growth stopped. Not because of the arithmetic, it stopped because OPEC raised their oil prices. So we're asking, what if? Suppose the growth had continued. Let's go back to the year 1981. By 1981, on the 7% curve, the total usage in all of history would add up to 500 billion barrels, the remaining reserves 1,500 billion. The reserves at that point are 3 times the total of all that have been used in all of history. That's an enormous reserve. But what time is it when the remaining reserve is 3 times the total of all you've used in all of history? And the answer is 2 minutes before 12. Well, we know for 7% growth, the doubling time is 10 years. We go from 1981 to 1991. By 1991, on the 7% curve, the total usage in all of history would add up to 1,000 billion barrels. There'd be 1,000 billion left. At that point, the remaining oil would be equal in quantity to the total of all that we had used in something like 130 years of the oil industry on this earth. By most measures, you'd say that is an enormous remaining reserve. But what time is it when the remaining reserve is equal to all that you've used in all of history? And the answer is it's 1 minute before 12. So we go one more decade to the turn of the century. That's like right now. That's when 7% would finish using up the oil reserves of the earth. Now let's look at this in a very nice graphical way. Suppose the area of this tiny rectangle represents all the oil we used on this earth before 1940. Then in the decade of the 40s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 50s, we used this much. That's equal to the total of all that have been used in all of history. In the decade of the 60s, we used this much, and again, that's equal to the total of all the preceding usage. Now, here we see graphically what President Carter told us. Now, if that 7% had continued through the 70s, 80s, and 90s, there's what we need. But that's all the oil there is. Now, there's a widely held belief that if you throw enough money at holes in the ground, oil is sure to come up. Well, there will be discoveries in new oil. There may be major discoveries, but look, we have to discover this much new oil if we would have that 7% growth continue 10 more years. Well, ask yourself, what do you think is the chance that oil discovered after the close of our class today will be in an amount equal to the total of all that we've known about in all of history? And then realize if all that new oil could be found, that would be sufficient to let the historic 7% growth continue 10 more years. Well, it's interesting to read what the experts say. Here's an interview in Time magazine with one of the most widely quoted oil experts in all of Texas. They ask him, but haven't many of our bigger fields been drilled nearly dry? He responds saying there's still as much oil to be found in the U.S. as has ever been produced. Now let's assume he's right. What time is it? And the answer is it's 1 minute before 12. I've read several things this guy's written. I don't think he has any understanding of this very simple arithmetic. Well, in the crisis back in the 70s, ads such as this appeared. This is from the American Electric Power Company. It was a bit reassuring, sort of saying, now don't worry too much, because we're sitting on half of the world's known supply of coal, enough for over 500 years. Now, where did that 500-year figure come from? Well, it may have had its origin in this report to the Committee on Interior and Insular Affairs of the United States Senate, because in that report we find this sentence. At current levels of output and recovery, these American coal reserves can be expected to last more than 500 years. There is one of the most dangerous statements in the literature. It's dangerous because it's true. But it isn't the truth that makes it dangerous. The danger lies in the fact that people take the sentence apart. They just say coal will last 500 years. They forget the caveat with which the sentence started. And what were those opening words? At current levels. Now, what does that mean? It means if and only if we maintain zero growth of coal production in this country. So let's look at a few numbers. We go to the annual energy review published by the U.S. Department of Energy. They give this figure as the coal demonstrated reserve base, and it carries a footnote that says about half the demonstrated reserve base is estimated to be recoverable. You cannot recover and use 100% of the coal that's in the ground. So this number is half of this number, and we'll come back to those in just a moment. Now, the report also tells us that in the year 1971, we were mining coal in this country at this rate. 20 years later, 1991, we were mining at this rate. Put those numbers together, and the average growth rate of coal production in those 20 years was 2.86% per year. And so we have to ask, well, how long could a resource last if you had steady growth in the rate of consumption till the last bit of it was used? Well, I'll just show you that equation. For the expiration time, I'll tell you, it takes first-year college calculus to derive that equation, so it can't be very difficult. You know, I have the feeling there must be dozens of people in this country who have had first-year college calculus. But let me suggest, I think that equation's probably the best-kept scientific secret of the century. Now, let me show you why. If you use that equation to calculate the life expectancy of the reserve base, or of the 1/2 the reserve base that's estimated to be recoverable, for different steady rates of growth, you find if the growth rate is 0, the small estimate would go about 240 years. The large one would go close to 500 years. So that report to the Congress was correct. But look what we get when we plug in steady growth. Back in the 1970s, we had national goal of achieving 8% per year growth rate in coal production in the United States. If that could be achieved and continued, coal would last between 37 and 46 years. President Carter cut that goal roughly in half, hoping to reach 4% per year. If that could continue, coal would last between 59 and 75 years. Here's that 2.86 that we just saw, the average for a recent 20-year period. If that could continue, coal would run out between 72 and 94 years. That's within the life expectancy of children born today. The only way we're going to get anywhere near this widely quoted 500-year figure is to do simultaneously two highly improbable things. Number one, we've got to figure out how to use 100% of the coal that's in the ground. Number two, we've got to figure out how to have 500 years of zero growth of coal production. Now, these are simple facts. Just look at those numbers. I got a report recently from the coal fields of Kentucky, West Virginia, Virginia, these giant bituminous coal fields that supply a large fraction of the electricity in the eastern United States. They estimate that maybe they have another 30 years of coal mining before it will become uneconomical to mine there. And then what will we do when we want to switch on the lights? Let's now go back and note that in the 1970s there was great national concern about energy, but this concern disappeared in the 80s. Now, the concerns about energy in the 70s prompted experts, journalists, and scientists to assure the American people that there was no reason to be concerned. So let's go back now and look at some of those assurances from the 70s so we can see what to expect as the energy crisis returns. Here is the director of the Energy Division of the Oak Ridge National Laboratories. He's telling us how expensive it is to import oil, telling us we must have big increases in our use of coal. Under these conditions, he estimates America's coal reserves are so huge they could last a minimum of 300 years, probably a maximum of 1,000 years. Now, you've just seen the facts. Now you see what an expert tells us, and what can you conclude? There was a 3-hour television special on CBS on energy. The reporter said by the lowest estimate, we have enough coal for 200 years, but the highest enough for more than 1,000 years. You've just seen the facts. Now you see what a journalist tells us after careful study. And what can you conclude? In the Journal of Chemical Education, on the page for high school chemistry teachers, an article written by the scientific staff of the journal, we read that our proved coal reserves are enormous, and they give a figure. These could satisfy present U.S. energy needs for nearly 1,000 years. Let's do long division. You take the coal they say is there, divide by what was then the current rate of consumption, and you get 180 years. Now, they didn't say current rate of consumption. They said present U.S. energy needs. Coal today supplies about 1/5, around 20% of the energy that we use in this country. So if you'd like to calculate how long this quantity of coal could satisfy present U.S. energy needs, you have to multiply this denominator by 5. When you do that, you get 36 years. They said nearly 1,000 years. Newsweek magazine, in a cover story on energy, said at present rates of consumption, we have enough coal for 666.5 years. And the 0.5 means they think it'll run out in July instead of January. Now, if you round that off and say roughly 600 years, 600 is close enough to 500 to lie within the uncertainty of our knowledge of the size of the resource. So with that observation, that is a correct statement. At present rates, meaning zero growth, we have enough coal for around 600 years. The whole point of the story that this led into was that we have to have rapid growth in coal consumption in the United States. Now, it's obvious, isn't it? If you have the growth they're writing about, it won't last as long as they said it would last with zero growth. They never mentioned this. I wrote them a long letter, told them I thought this was a serious misrepresentation, to give the readers the feeling that we can have all the growth that they're writing about and still have coal around for 650 years. I got back a nice form letter. It had nothing to do with what I'd tried to explain to them. I gave this talk at a high school in Omaha, and after the talk, the high school physics teacher came to me, and he had a booklet. He said, have you seen this? I hadn't seen it. He said, look at this. We've got coal coming out of our ears. As reported by Forbes magazine, now that's a prominent business magazine, the United States has 437 billion tons of known coal reserves. That is a good figure. This is equivalent to a lot of BTUs, or it's enough energy to keep 100 million large electric generating plants going for the next 800 years or so. Now, the teacher said to me, how can that be true? That's one large electric generating plant for every 2 people in the United States. I said, of course it can't be true. It's absolute nonsense. Let's do long division to see how crazy it is. So you take the coal they say is there, divide by what was then the current rate of consumption, you find you couldn't keep that rate up for 800 years. We hardly have 500 large electric generating plants. They said it would be good for 100 million such plants. Time magazine tells us that beneath the pits heads of Appalachia and the Ohio Valley, and under the sprawling strip mines of the West, lie coal seams rich enough to meet the country's power needs for centuries, no matter how much energy consumption may grow. And so I give you a very fundamental observation. Don't believe any prediction of the life expectancy of a non-renewable resource until you have confirmed the prediction by repeating the calculation. As a corollary, we have to note that the more optimistic the prediction, the greater is the probability that it's based on faulty arithmetic or on no arithmetic at all. Again, from Time magazine, energy industries agree that to achieve some form of energy self-sufficiency, the U.S. must mine all the coal that it can. Now think about that for just a moment. Let me paraphrase it. The more rapidly we consume our resources, the more self-sufficient we'll be. Now, isn't that what it says? Well, David Brower called this the policy of strength through exhaustion. Now, here's an example of strength through exhaustion. Here is William Simon, energy advisor to the President of the United States. Simon says we should be trying to get as many holes drilled as possible to get the proven oil reserves. The more rapidly we can get the last of that oil up out of the ground and finish using it, the better off we'll be. Well, let's look at Dr. Hubbard's graph for oil production in the lower 48 states. There was a long period of approximately steady growth indicated by this straight line on the semi-logarithmic plot. But for quite a while now, production has fallen below the growth curve while our demand continued on up this growth curve until the 1970s. Now, it's obvious the difference between those two curves has to be made up with imports. And it was in early 1995 that the news told us that the year 1994 was the first year in our nation's history in which we had to import more oil than we were able to get out of our own ground. Well, maybe you're wondering, does it make any sense to imagine that we could have steady growth in the rate of consumption of a resource till the last bit of it was used and then the rate of consumption would plunge abruptly to zero? I say no, that does not make sense. You say, all right, why bother us then with the calculation of this expiration time? My answer is this: every segment of our society, our business leaders, government leaders, political leaders, the local level, state level, national level, everyone aspires to maintain a society in which all measures of material consumption continue to grow steadily, year after year after year, world without end. Now, since that's so central to everything we do, we ought to know where it would lead. On the other hand, we should recognize there is a better model. We turn again to the work of the late Dr. Hubbard. He has plotted the rate of consumption of resources that have already expired. He finds, yes, there is an early period of steady growth in the rate of consumption, but then the rate goes through a maximum and comes back down in a nice symmetric bell-shaped curve. And when he fitted this curve to the data on U.S. oil production back in the 1970s, he found that at that point we were right about there. We were halfway through that enormous resource. Now, that's roughly what that Texas expert said in the quotation we saw earlier. Now let's see what it means. It means that from now on, domestic oil production can only go downhill, and it's downhill all the rest of the way. And it doesn't matter what they say inside the Beltway in Washington, D.C. Now, it means we could work hard and put some bumps on the downhill side of the curve. You'll see there are bumps on the uphill side. The debate is heating up over drilling in the Arctic Wildlife Refuge. I've seen the estimate that they might find 3.2 billion barrels of oil up there. 3.2 billion is the area of that little tiny square. That's less than 1 year's consumption in the United States. Now, let's look at the curve in this way. The area under the entire curve represents the entire resource of U.S. petroleum before any of it was used. Now, that area has been divided here into three parts. Unshaded on the left, that's the oil we've taken from the ground. We've used it, it's gone. This vertical shaded band, that's the oil we've drilled into. We've found it, we're pumping on it today. Shaded in green on the right is the undiscovered oil. We have very good ways now of estimating how much oil remains undiscovered. This is the undiscovered oil. This is the oil we're looking for in all those places where drilling is going on. This is the oil we've got to find if we're going to make it down the curve on schedule. Now, every once in a while someone reminds me that 100 years ago someone did a calculation and predicted that the U.S. would be out of oil perhaps in 25 years. We obviously were not. The calculation must have been wrong. Therefore, of course, all calculations are wrong. Well, now let's understand what they did 100 years ago. This band of discovered oil 100 years ago was way over in here someplace. At that point, they had no idea how much oil was undiscovered. So they just took the discovered oil, divided by how rapidly it was then being consumed, come up with 25 years. Now, it's clear you have to make a new calculation every time you make a new discovery. We're not asking today how long will the discovered oil last. We're asking about the discovered and the undiscovered. We're now asking about the rest of the oil. And what does the Geological Survey tell us? Back in 1984, they said that the estimated supply in the U.S. from undiscovered resources and demonstrated reserves is 36 years at present rates of production, or 19 years in the absence of imports. 5 years later, in 1989, that 36 years is down to 32 years. The 19 years is down to 16 years. So the numbers are holding together as we march down the right-hand side of the Hubbard curve. So maybe you're wondering, well, why didn't somebody tell us this? It was back in 1956. Dr. Hubbard addressed a convention of petroleum geologists and engineers. He told them that his calculations led him to conclude that the peaks of U.S. oil and gas production that you just saw can be expected to occur between 1966 and 1971. No one took him seriously. So let's see what's happened. The data here are from the Department of Energy. So this is U.S. oil production. We see a long period of approximately steady growth. Here's the year 1956 when Dr. Hubbard did his analysis, and he said at that time that the peak would occur between 1966 and 1971. Well, the peak occurred in 1970. It was followed by a very rapid decline. Then the Alaska pipeline started delivering its first oil, and there was a partial recovery. That production has now peaked, and everything's going downhill in unison. And when I go to a spreadsheet on my computer at home, and I find the parameters of the curve that is the best fit to these scattered U.S. data, from that best fit curve, it looks to me as though we have consumed 3/4 of the recoverable oil that was ever in our ground, and we're now coasting downhill on that last 25% of the oil. Well, we have to ask, what's the Department of Energy doing about this? And here in 1998, we read about a new comprehensive national energy strategy, a set of policy goals that include halting the slide in U.S. oil production by the year 2005. Now ask yourself, what do you think is the chance that we can do anything more than put a little bump on the downhill side of the curve? Well, what does this mean? Let's look at the definition of modern agriculture. It's the use of land to convert petroleum into food. And we can see the end of the petroleum. Well, we have to ask about world petroleum. And in 1972, Dr. Hubbard produced this curve, and he suggested that he thought the peak of world production would occur around 1995. So we have to go to the data and see what has happened. Here, again, from our Department of Energy, but this now is world oil production, and we can see a long period of steady growth of oil production. There was quite a major drop right there. Then there was a recovery, then simply an enormous drop, and a partial recovery here. So it's clear we're not yet over the peak. Each of those drops that you saw there was due to a price hike from OPEC. And I think that those drops in delaying the arrival of the peak are the reason for the fact that the peak will occur later than Dr. Hubbard had projected it to be. Well, I go back to my spreadsheet on my computer at home, and now in addition to just fitting the curve, since the curve has not started down, I can't get a very good fit for the curve for the area under the curve. But what I have to do then is to go to the geology literature and find out what is the consensus figure among geologists as to the total amount of oil we'll ever find on this earth. Well, this consensus figure is 2,000 billion barrels. Now that's uncertain. It has an uncertainty maybe 40%, plus or minus 40%, so it's a very uncertain figure. But that's the consensus figure. If I do that and do the fit, there is the curve. The curve has a peak in the year 2004. Now if I say, let's assume there's 50% more oil than the geology consensus, then the fit gives me the year 2019 for the peak, and if I assume there's twice as much oil as the consensus figure, then the peak's back to the year 2030. Now look at those curves. In your life expectancy, you are going to see the peak of world oil production. And you've got to ask yourself, what's life going to be like on this earth when we have production declining and we have a growing population and a growing per capita demand for oil? Now just think about it. This isn't rocket science. This is something that we can all think about. In the March issue of Scientific American for the year 1998, there was a major article by two real petroleum geologists. One's in England, one's in France. They said that their estimate for this peak was that it would occur before the year 2010. So their estimate and the one I'm showing you here that I've made, these are in the same ballpark, and we're talking about the same kind of numbers. Now that analysis that was in Scientific American caused a lot of discussion. And in particular, in Fortune magazine in 1999, commenting on this scientific analysis that was done by petroleum geologists, we find an emeritus professor of economics at MIT saying that this analysis is a piece of foolishness. The world will never run out of oil, not in 10,000 years. And so we have non-scientists telling us that petroleum reserves are greater than ever before in history, and we have geologists telling us that we're finding only 1 barrel of new oil for every 4 barrels we take out of the ground and consume. What is going on here? You've seen the figures. Here in 1999, U.S. lower 48 state January oil output hit a 50-year low, exactly what you expect as you're going down the right-hand side of the Hubbard curve. And one of Dr. Hubbard's favorite graphs is this one. And this is on a time scale from 5,000 years ago to 5,000 years in the future, and the age of fossil fuels is a little blip in the middle of the screen. Think about it. Well, we have to ask about new discoveries. Here in 1993, we read about the largest oil discovery in the Gulf of Mexico in the past 20 years, an estimated 700 million barrels of oil. Now that's a lot of oil, but a lot compared to what? At that point, we were consuming in the United States 16.6 million barrels of oil every day. Do the long division and you find that entire discovery would serve our needs for 42 days. And that's the biggest discovery they've made in the Gulf of Mexico in 20 years. On the front page of the Wall Street Journal in 1997, we read about the new Hibernia oil field off the south coast of Newfoundland. Please note this one line in the headline: now it will last 50 years. And let's go to that story in the Wall Street Journal and read about the Hibernia field. It's one of the largest oil discoveries in North America in decades. It should deliver its first oil by the end of the year. At least 20 more fields may follow, offering well over 1 billion barrels of high-quality crude, promising a steady flow of oil will be just a quick tanker run away from the energy-thirsty East Coast. They may find 1 billion barrels of oil in that undersea deposit. So 1 billion barrels, we're now consuming something like 18 million barrels a day. Do the long division, and that whole supply would meet our needs in the United States for 56 days. And what did that headline say? It said 50 years. Well, some people say there's nothing to worry about. And here we have a very prominent figure who says that we should grow corn, distill it into ethanol, and we can run the entire fleet of U.S. vehicles on ethanol derived from corn. And in support of this, he says today ethanol production displaces over 43.5 million barrels of imported oil annually. Now that sounds pretty good until you think. Now the first thing that you have to do is to ask, okay, 43.5 million, what fraction is that of the annual consumption of petroleum in vehicles in the United States? And the answer is it's 1%. You'd have to multiply corn production devoted to ethanol by a factor of 100 just to make the numbers come out right. And I've seen the suggestion that that would take all of the agricultural land in the United States. Now the second problem is it takes diesel fuel to plow the ground to plant the corn. It takes fossil fuels to make the fertilizer to make the corn grow. It takes more diesel fuel to tend the corn and to harvest the corn. It takes more energy to do the distillation. You finally get a gallon of ethanol. You will be lucky if there's as much energy in the gallon of ethanol as it took to produce it. It's a loser. Yet this guy says, don't worry, everything will be all right. Well, there's a lesson here, and the lesson is that we cannot let other people do our thinking for us. Let's take another look at world oil production. Now the graph here is slightly different from the one I showed earlier. What I'm showing here is per capita production of oil, which means that at every point I take the world production divided by the world population that year. Now the scale here on the vertical axis is liters per person each day. There's the number 2. Now 2 liters a person a day, 2 liters is about half a gallon. Now notice that the peak occurred in the 1970s, and it's been going downhill, and in the 1970s it was a little over 2 liters a person a day, and now it's down to about 1.7 liters per person each day. So we can say with confidence that any day that any one of us uses more than 1.7 liters of petroleum, directly or indirectly, we're using more than our share. Now, what's the average consumption in the United States? And the answer is it's up around 8 liters a person a day. So think about the inequity that's represented there. Now, there's something even more important in this graph. That peak in the 1970s, I think that historians in the future will look back at this peak and say that was a major turning point in all of human history. That's the point where per capita consumption of petroleum reached its peak before it started its inevitable decline, and there isn't any way I can see that we can reverse that trend, that downward trend, given the world population growth and given the fact that we're right close to the peak of world production. Well, Dr. Hubbard addressed a committee of the Congress. He told them that the exponential phase of the industrial growth, which has dominated human activities during the last couple of centuries, is now drawing to a close. Yet during the last 2 centuries of unbroken industrial growth, we have evolved what amounts to an exponential growth culture. I would say it's more than a culture, it's our national religion, because we worship growth. Pick up any newspaper, you'll see headlines such as this: State forecast robust growth. Have you ever heard of a physician diagnosing a cancer in the patient and telling the patient you have a robust cancer? We had Americans being killed in the Gulf War. What's this person worried about? He doesn't care about people. He doesn't care about people being killed. All he's worried about is, oh, the Gulf situation may hurt Colorado's growth. Now, this incredible addiction is not limited to the United States. The Wall Street Journal tells us that the Japanese are so accustomed to growth that economists in Tokyo usually speak of a recession as any time the growth rate dips below 3% per year. So what do we do? In the words of Winston Churchill, sometimes we have to do what is required. We must educate all of our people to an understanding of the arithmetic and the consequences of growth, especially in terms of populations and in terms of the Earth's finite resources. We must educate people to recognize the fact that growth of populations and growth of rates of consumption of resources cannot be sustained. Now, the world is full of people who are yakking about sustainability. Now, some of them are doing serious good things, like trying to reduce energy consumption and things like this. Some of them are just trying to attack the word sustainability onto whatever they're doing, whether it's sustainable or not. We've got to understand the first law of sustainability, and it follows directly from what I've just been talking about. The first law of sustainability is this: population growth and or growth in the rates of consumption of resources cannot be sustained. Now, this follows from the arithmetic of steady growth that we've spent time developing. So this isn't an opinion. Opinions are debatable. This is fact. There's nothing here to debate. You cannot sustain population growth. You cannot sustain growth in the rates of consumption of resources. And so it's intellectually dishonest to talk about sustainability without stressing the obvious fact that stopping population growth is a necessary condition for sustainability. Now, it's not sufficient. Stopping population growth in itself is not sufficient, but there's no way you can have sustainability if you don't stop population growth. We need to educate people to see the need to examine carefully the allegations of the technological optimists who assure us that science and technology will always be able to solve all of our problems of population growth, food, energy, and resources. Now, chief among these optimists was the late Dr. Julian Simon, formerly professor of economics and business administration at the University of Illinois and later at the University of Maryland. With regard to copper, Simon has written that we will never run out of copper because copper can be made from other metals. Well, the letters to the editor jumped all over him, told him about chemistry. He just brushed it off. He said, don't worry. If it's ever important, we'll figure out how to make copper out of other metals. Simon had a book that was published by the Princeton University Press, and in that book he's writing about oil from many sources, including biomass, and he says clearly, there's no meaningful limit to this source except for the sun's energy. He goes on to note, but even if our sun were not so vast as it is, there may well be other suns elsewhere. Simon's right. There are other suns elsewhere. But now the question is, would you base public policy on the belief that if we ever need another sun, we'll figure out how to go get it and haul it back into the solar system? Now don't laugh. For decades before his death, this man was a trusted policy advisor at the very highest levels in Washington, D.C. Here's a quotation from one of his strong supporters. There was a UN report that talked about the possibility of resource collapse because of population growth, and when asked about the report, HUD Secretary Jack Kemp said, nonsense, people are not a drain on the resources of the planet. Malcolm Forbes Jr., editor-in-chief of Forbes magazine, tells us in an editorial that CNN recently ran a silly series purporting to show that the world's in mortal danger because there are too many of us. In the poorer countries, the many mouths mean poverty, and richer countries are wrecking the Earth's atmosphere with pollution. It's all nonsense. Bill Moyers interviewed Isaac Asimov. He asked Asimov, what happens to the idea of the dignity of the human species if this population growth continues? And Asimov says it'll be completely destroyed. I like to use what I call my bathroom metaphor. If two people live in an apartment and the two bathrooms and both have freedom of the bathroom, you can go to the bathroom anytime you want, stay as long as you want for whatever you need, and everyone believes in freedom of the bathroom. It should be right there in the Constitution. But if you have 20 people in the apartment and two bathrooms, then no matter how much every person believes in freedom of the bathroom, there's no such thing. You have to set up times for each person. You have to bang on the door, aren't you through yet, and so on. And Asimov concluded with what I think is one of the most profound observations I've seen in years. Asimov says, in the same way, democracy cannot survive overpopulation. Human dignity cannot survive overpopulation. Convenience and decency cannot survive overpopulation. As you put more and more people into the world, the value of life not only declines, it disappears. It doesn't matter if someone dies. The more people there are, the less one individual matters. Now let me give you two examples of this destruction of democracy by population growth. I joined the faculty here in 1950. At that time, the population of Boulder was about 20,000. There were 9 members of the city council. Today it's approaching 100,000. There are 9 members of the city council. So in a little over 50 years, the number of people per member of the city council has increased by a factor of 5. Democracy in Boulder has declined to 20% of what it was 50 years ago. And the second example has to do with the year 2000 national census. This showed that in the decade of the 90s, the U.S. population increased by about 13%. Now this means every House seat in the House of Representatives now has 13% more constituents on the average than they did 10 years ago. And in the last 1 hour, the world population has increased by about 10,000 people, and the population of the United States in this 1 hour has increased by about 280 people. And we have to ask, why don't more U.S. environmentalists and environmental organizations speak out about the problem of population growth here in the United States? The simple arithmetic makes it absolutely clear that long-term preservation of the environment in the U.S. is impossible in the face of continued U.S. population growth. But you hear all sorts of political leaders say, oh, we can have our growth, we'll call it smart growth, and smart growth will save the environment. Well, we need to know about smart growth. Smart growth destroys the environment. Dumb growth destroys the environment. Now, smart growth just destroys the environment with good taste. So it's a little like buying a ticket on the Titanic. If you're smart, you go first class. If you're dumb, you go steerage, but the result's the same. So central to the things that we must do is to recognize that population growth is the immediate cause of all of our resource and environmental crises. And of all the crises, I think this one, global warming, looms larger and more threatening than anything in all of human history. Now, because of our enormous per capita consumption of resources, we can say with confidence, the world's worst population growth problem is right here in the United States. But you hear all sorts of well-meaning people pointing to distant underdeveloped nations and saying they're the problem with overpopulation. The average person in the United States in a lifetime will consume something like maybe 30 times the amount of resources that'll be consumed by a person in a lifetime in an underdeveloped nation. We are the problem. We have the responsibility, and we have the authority to deal with the problem here as a domestic problem in the United States. And some years ago, speaking here on the campus of the University of Colorado, our United States Senator Tim Wirth said that the best thing we can do to help other countries stop their population growth is for us to set an example and stop our own population growth here in the U.S. We have sent representatives to international conferences to tell the underdeveloped nations, you're the problem, you've got to stop your population growth. And they just laugh and say, look, you're the problem with all of your high per capita consumption. Now, except for the petroleum graphs, the things I tell you are not predictions of the future. I'm only reporting facts and the results of some very simple arithmetic. But I do this with confidence that these facts, this arithmetic, and more important, our level of understanding of them will play a major role in shaping our future. Now, don't take what I've said blindly or uncritically because of the rhetoric or for any other reason. Please, you check the facts. Please check my arithmetic. If you find errors, please let me know. But if you don't find errors, then I hope you'll take this very, very seriously. You are important people. You can think. And if there was ever a time when the human race needs people who will think, it's right now. It's our responsibility as citizens in a democracy to think. And so to be successful with this experiment of human life on Earth, we have to understand the laws of nature as we encounter them in the study of science and mathematics. We have to remember the message of this cartoon. Thinking is very upsetting. It tells us things we'd rather not know. We should remember the words of Galileo. He said, I do not feel obliged to believe that the same God who has endowed us with sense, reason, and intellect has intended us to forego their use. We should remember the words of Aldous Huxley. He observed that facts do not cease to exist because they're ignored. And we should remember H.L. Mencken's social philosophy. He believed that it was in the nature of the human species to reject what is true but unpleasant and to embrace what is obviously false but comforting. And we should remember Eric Severide's law. He was a newscaster who made the transition from radio to television back in the 1950s. He observed that the chief source of problems is solutions. Now let's just look at an example. The Nile River for thousands of years would flood in the spring, and the silt that was carried down by the river would be deposited on agricultural lands on the two sides of the river, and this renewed the fertility of the land. They had a sustainable agriculture for thousands of years. But now the flood was kind of a nuisance as you had cities develop along there, and the city people didn't like the floods, and then the city people needed electricity. So that was the problem. What was the solution? The high dam at Aswan. So now let's look at the problems caused by the solution. First of all the silt is carried down by the river, is deposited in the reservoir behind the dam. So this means the dam has a lifetime, maybe 100 to 200 years. It certainly is not very long. So it'll be filled, and then there won't be the storage capacity that it was designed to have. The water that's let out from the dam today is very clear water. So this means all of the erosion patterns downstream have changed. It used to be deposit here, pick up there, and so on. Now it's pretty much just picking up because it starts out from the dam as clear water. Down at the delta in Alexandria, where the Nile enters the Mediterranean Sea, they're washing away agricultural land because it's no longer being deposited and the river is just washing it out into the Mediterranean. And it used to be the load of biological nutrients that were brought down in this river all the time supported a major fishery in the eastern Mediterranean. That fishery is in serious decline because the nutrients no longer reach there. And now, in order to have their agriculture, they've got to do irrigation. They've got to buy fertilizer. It takes energy to make the fertilizer, and it could easily be that some of the energy to make the fertilizer comes from the dam. And now there are lots of more agricultural workers wading barefoot in the irrigation ditches, and they're subject to a schistomiasis, which is some kind of a parasite that's carried by things in the water that can get through the skin. And if you're barefoot in the water, why you can get this. Everything went bad because of the solution to the problem. Nobody looked at what the problems would be caused by the solution. This is one of the most important things that we need to remember. Now, here's a challenge. Can you think of any problem on any scale, from microscopic to global, whose long-term solution is in any demonstrable way aided, assisted, or advanced by having larger populations at the local level, at the state level, the national level, or globally? Can you think of anything that will get better if we crowd more people into our communities, into our state, into our nation, or on this earth? Think about it. Will anything get better with increased population? And I like the words of the late Reverend Martin Luther King, Jr. He said, unlike the plagues of the Dark Ages or contemporary diseases which we do not yet understand, the modern plague of overpopulation is soluble by means we have discovered and with resources we possess. What is lacking is not sufficient knowledge of the solution, but universal consciousness of the gravity of the problem and the education of the billions who are its victims. And so I hope I've made a reasonable case for my opening statement that I believe the greatest shortcoming of the human race is our inability to understand this very simple arithmetic. So I thank you very, very much, and I'd be happy to answer questions.